All right, we're back now to talk about the differences in how we looked at initial conditions from circuits 1 to how we're actually going to start looking at initial conditions when we're considering circuits that involve two energy storing elements, specifically the inductor and the capacitor, basically working together. Now, in the past, we have basically considered just the initial conditions specifically of this form. The initial condition for the voltage across the capacitor, in which we just said VC of 0, or we would say IL of 0. There's a different way that we actually have to start looking at basically where these initial conditions exist within basically our dynamic timeline. Now, obviously, there's three portions of the timeline that we really have to concern ourselves with. Number one, the steady state conditions before the event happens. Remember, the event happens at t equals 0, in which we change that circuit topology. We change the schematic by opening or closing that switch. And by doing that, we change basically the amount of resistance or basically separate excitation to the capacitor and the inductor. So we have the initial steady state, in which we have basically our initial condition for the voltage across the capacitor or the current through the inductor. With the transient phase, that's when we actually start exhibiting that change within the circuit. And so we actually see basically that voltage across the cap or the current basically start to change. And that's generally what we're modeling in this class. And then eventually we go through that transient period in which the circuit then regains a steady state and basically exhibits either a final voltage across the capacitor or a final current through the inductor. And sometimes we just say that it dies off. But basically, steady state, we invoke a change and go through a transient period, and then we actually come back and regain that steady state. But there's a different way that we actually have to start looking at the timeline. Now, remember from last semester, we talked a lot about t is equal to 0, invoking that change. Now we're actually going to be considering two different portions of time in reference to t equals 0, and that's t equals 0 minus and t equals 0 plus. And really what that means for us, t equals 0 minus is that instance right before that switch is open or closed, okay? Right before that switch is open and closed. T is equal to 0 plus, that is actually more in reference to that instance right after that switch opens or closes. And the reason why we concern ourselves with that is because the voltage across the capacitor and the current through the inductor cannot instantaneously change. They absolutely cannot instantaneously change. So whatever we had for t less than 0, okay, remember that this time period right here is t less than 0, is VC of 0 minus or IL of 0 minus. Basically the voltage across the cap or the current through the inductor are both seen in steady state. If they're both in steady state, obviously this is where we gain those initial conditions, and right after that instance, right after that switch opens or closes, t equals 0 plus, that's when we actually see VC of 0 plus or IL of 0 plus. That voltage and current can't instantaneously change. During that transient period, though, we will start seeing a rate in which basically the voltage or the current can actually start changing through basically that transient period as we start seeing exponential forms or even when we actually start seeing an oscillation in the exponential form of the response. And eventually, once we actually gain into the steady state again, we have VC of infinity, IL of infinity. But what does this represent right here? Well, if we normally think of VC of 0 plus and IL of 0 plus, those are going to be constants, right? Those are going to be constants that we are going to find from basically analyzing the circuit with the voltage, with the cap acting like an open circuit or the inductor acting like a short circuit. These right here don't represent necessarily just, the derivative of those initial conditions, because the derivative of a constant would just be 0. Not necessarily in this case, and we're going to see why that is not the case in just a second. These basically represent a rate of change in which we actually see this being measured in terms of volts per second, and here the IL of 0 plus dt is amps per second. So these are the true initial conditions that we're going to be utilizing when we actually set up our differential equation. And second, the differential equation, because of those two energy storage elements, are actually going to be of a second order. So therefore, two energy storing elements, second order differential equation, we have to have two initial conditions. And those are going to be for the capacitor, Vc of 0 plus, that voltage that can't instantaneously change, and then actually the rate of change of that initial condition. So these are the two that we would actually utilize for the second order equation that represents the response for the voltage across the capacitor. And these are the two that we would actually utilize for the response of the current through the inductor. But again, T is equal to 0 plus is that instance right after that switch is changed. Everything from here back is steady state, and we know that can't change. But here, this is where we actually exhibit that change within that circuit. We see that dynamic response in which we eventually settle back into a steady state for T is equal to infinity. How do we actually find these? If I say we can't just take the derivative of a constant, we actually may get some form of value from that. Let's take a look at basically how we would actually determine those values. Now again, voltage across the cap can't instantaneously change. Current through the inductor can't instantaneously change, but maybe there's other portions of those current voltage characteristics that can actually change instantaneously. Let's take a look. All right. So now going back here, let's consider once again Vc of 0 minus would be equal to Vc of 0 plus, and IL of 0 minus is equal to IL of 0 plus, because those elements, that voltage across the capacitor or current through the inductor, can't instantaneously change. And due to that notion, these values will be the same. Now what about the change in those initial conditions? Well, these can't instantaneously change, right? Voltage across the capacitor can't instantaneously change. Current through the inductor can't instantaneously change. And that's due to the capacitor's electric field as well as the magnetic field of the inductor. So how do we find these rates of change that we would actually see exhibit? So DIL of 0 plus or dVc of 0 plus dt. Well, it's easy to find those because essentially what we do is take the current voltage characteristic of the capacitor and the current voltage characteristic of the inductor, and we just evaluate those at t equals 0 plus. So what that means is DIL of 0 plus dt is equal to VL of 0 plus divided by L. It's just nothing more than that current voltage characteristic evaluated at t equals 0 plus. Here, dVc 0 plus dt is equal to IC of 0 plus divided by C. Here's the thing. We can find these values. We can find these rates of change because VL of 0 plus is in fact actually something, a characteristic within the inductor that can instantaneously change. And we can actually find that quite simply. IC of 0 plus, absolutely. When we actually want to develop a voltage across the anode and the cathode, then positive charge has to go and collect on that anode, and negative charge has to collect on the cathode. And this really means that in order to actually get that charge there, current through the capacitor has to be instantaneous. That has to have the ability to even get there instantaneous, to develop that charge on those two plates in order to set up that potential difference. So we can't just go through and just easily find a steady state condition for VL of 0 plus or IC of 0 plus because we actually may have to do a little bit of extra work to see how maybe another element may be impacting those values, or maybe how we're going to evaluate a KVL or KCL equation in order to actually gain those values themselves. Now, for series and parallel, they're easy to take a look at. And by the way, we can find these guidelines. I highly recommend utilizing this page of guidelines on page 9 in the supplemental text, because this is actually going to help streamline basically you working through your problems in order to actually determine these initial conditions. This usually seems to be a very conceptual issue for students sometimes in this class, but we got some guidelines here, and as we work through example problems, we're actually going to see how this is actually not as confusing as I think some think it is up front. It's a lot of info. In this class, there's so much information that we have to go over in order to be successful and master these concepts. But maybe if we can streamline it a little bit and have a few guidelines, it will make working through all of our example problems very, very simplistic. Now, so dVc of 0 plus dt for series elements is equal to Ic of 0 plus divided by C. But for series elements, all the currents are going to be the same. So the current through the inductor is actually going to be the same as the current through the capacitor. So in this case, Ic of 0 plus divided by C is actually going to be equal to IL of 0 plus divided by C because of that series nature. Series elements have the same current, obviously different values for voltage. For here, DIL of 0 plus dt, VL of 0 plus divided by L. Well, VL of 0 plus can actually instantaneously change, and in order for us to find that for series elements, we have to basically look at the KVL equation and evaluate that at t equals 0 plus. So Vc of 0 plus VL of 0 plus VR of 0 plus, and that's equal to Vs. So just a quick evaluation of the KVL equation will render us a form of VL of 0 plus that we can utilize within our differential equation analysis. Now parallel, dVc of 0 plus dt is equal to Ic of 0 plus divided by C. Very similarly to finding the change in the initial condition for the current through the inductor, we find Ic of 0 plus because it can instantaneously change by looking at the KCL equation and evaluating that at t equals 0 plus. So Ic of 0 plus IL of 0 plus IR of 0 plus is equal to Is. Sometimes it's going to be equal to 0. And so we can just easily go through and find Ic of 0 plus. Now, due to the parallel nature, voltages are the same currents or not. So DIL of 0 plus dt is equal to VL of 0 plus divided by L, which is equal to Vc of 0 plus divided by L. Here, the voltage across the inductor, that initial condition right there is actually going to be the same as the voltage across the capacitor, because that voltage across the capacitor is going to drive this value just similarly in such a way that the inductor, that initial current in the series elements, drove a value for the current through the inductor. Now, how we actually go through and develop these, obviously we're going to find through examples that we're going to be working throughout the class. But always come back to this video and just get a quick reminder of where these are actually coming from. So we're going to actually show these through a few example problems that we got coming up. And if you're a little bit confused right now, just hang on, because once we actually start working through these problems, it's going to come very, very clearly. So, all right. Example problems are coming up. We're going to go through some discussions over partial fraction expansion, give you some more tools, and then we're actually going to start working through some examples in which we develop initial conditions, the differential equation, and then we're actually going to start solving it. All right, see you then.